Hi, everyone. My name is Jennifer Hofmann, one of the ARC scholars from Stanford this year. Just a little bit of background on myself. I got my bachelor's at MIT in chemical engineering in 2018, and I'm now in the fifth year of my PhD at Stanford. My work focuses broadly on building computational models of biological fluids, like the cellular interior, and biologic therapeutics, like monoclonal antibodies. Today, I'll focus on a project in this first category, investigating the physics that limit how fast a cell can grow. Here we focus on the model organism E. coli, which can grow and divide rapidly, doubling in as little as 20 minutes. This means that it has to replicate all of its contents in this remarkably short time. The majority of these contents are proteins, and so it's unsurprising that the synthesis of proteins limits how fast a cell can grow. This process, called translation, happens in the crowded cytoplasm at ribosomes, which use information stored in mRNA to assemble amino acids into protein products. To do so, a molecule called a ternary complex must quickly drop off the matching amino acid in the correct order. Experiments have shown that the rate of this process speeds up by about twofold as cells grow faster, but precisely how the speed up occurs was unknown. We built a computational model of this process and tracked how long it takes for a ternary complex to find and react with its matching ribosome. Calculating an elongation time, we found that representing only entropic interactions, meaning that molecules simply cannot overlap, predicts the speed up in translation at faster cell growth rates. However, the absolute rates are still threefold too slow. We then looked at how other physical forces, like attractions, might close this gap by shortening the transport process. We implemented these attractions in our model and found that translation is sped up by more than twofold. But E. coli has 4 of these binding sites on so-called L7-L12 proteins. Why 4, though? Wouldn't having more be beneficial? We tested different numbers of binding sites in our model and showed that 4 L7-L12 optimizes a trade-off between ternary complex binding and mobility. More broadly, we looked at a set of 350 other bacteria for which minimal doubling times were known and binned them by the number of these L7-L12 proteins. We found that faster growing cells have fewer of these binding sites, suggesting that it might be useful for engineering cells to either grow and produce a product faster or identifying targets to slow the growth of pathogenic organisms. Thank you for your attention, and I'm looking forward to talking with you at the Scholar Symposium.